The fabric of spacetime holds secrets that defy our everyday understanding. Light speed, denoted as c, is a fundamental constant in physics, approximately 299,792,458 meters per second. It is a universal speed limit, a cosmic speed limit, if you will. Nothing in the universe can travel faster than the speed of light. This speed plays a pivotal role in our understanding of how the universe works. One of the reasons light speed is significant is because it defines the maximum speed at which information can travel. Since light is made up of photons, which are massless particles, it can travel at this incredible speed. This has profound implications for communication and the exchange of information in the universe. In addition to its role in communication, light speed also governs the behavior of space, time, and energy. According to Einstein's theory of relativity, space and time are interconnected in what is known as spacetime. Light speed acts as a cosmic speed limit in spacetime, influencing how we perceive the passage of time and the distances between objects. When an object accelerates towards light speed, it experiences several fascinating effects. Time dilation, for example, occurs as an object's perception of time slows down the closer it gets to light speed. Length contraction is another effect, where objects appear shorter in the direction of motion as they approach light speed. These phenomena are mind-boggling and challenge our everyday notions of time and space. Furthermore, light speed also affects an object's mass. As an object accelerates towards light speed, its mass appears to increase. This increase is due to the relationship between energy and mass described by Einstein's famous equation, E equals mc squared. The closer an object gets to light speed, the more energy is required to accelerate it further. In theory, as an object with mass approaches light speed, its mass would become infinitely large, making it impossible to reach or exceed light speed. According to Einstein's theory of relativity, time is not absolute but is instead relative to the observer's motion and gravitational field. When an object accelerates towards the speed of light, something extraordinary happens. Time itself slows down for that object. Let's imagine you're on a spaceship traveling at a significant fraction of the speed of light, while someone on Earth is observing you. From your perspective, time would appear to pass normally. However, to the observer on Earth, it would seem like time is passing much slower for you. This phenomenon is known as time dilation. The closer you approach the speed of light, the more pronounced the effect becomes. As your velocity increases, time appears to slow down relative to someone in a stationary position. This means that if you were to travel at a high fraction of the speed of light and return to Earth, you would have experienced less time than the people who remained on Earth. You would essentially have time traveled into the future. To understand time dilation more technically, we need to consider the spacetime fabric. According to Einstein's theory, spacetime is a unified entity, and the presence of mass and motion causes it to curve. When an object moves at high speeds, it affects the curvature of spacetime, leading to time dilation. This effect arises from the constant speed of light. As an object accelerates towards light speed, it requires more and more energy to propel it further. However, according to relativity, energy and mass are interchangeable. As you gain energy to approach light speed, your mass increases, and this mass-energy relationship affects the flow of time. Although time dilation occurs as you approach light speed, it's important to note that it becomes most significant when traveling at a substantial fraction of the speed of light. Reaching the exact speed of light is impossible for objects with mass, as it would require infinite energy. Length contraction, also known as Lorentz contraction, is a fascinating effect that occurs as an object approaches the speed of light. When an object accelerates towards light speed, its length in the direction of motion appears to shrink from the perspective of an observer in a stationary position. To understand length contraction, we need to delve into the concept of spacetime. According to Einstein's theory of relativity, spacetime is not a fixed and rigid framework, but rather a flexible fabric that can be distorted by mass and motion. When an object moves at high speeds, it influences the curvature of spacetime, leading to the observed effect of length contraction. Let's imagine you're aboard a spaceship traveling at a significant fraction of the speed of light. From your perspective, the spaceship's length remains unchanged. However, For an observer outside the spaceship, the length of the spaceship appears to shrink in the direction of motion. This contraction occurs because the fabric of spacetime itself is being distorted. As an object accelerates towards light speed, both space and time become intertwined and change in a way that preserves the constant speed of light. The contraction of space in the direction of motion compensates for the time dilation effect we discussed earlier. The amount of length contraction experienced depends on the velocity relative to the observer. As an object's velocity approaches the speed of light, the contraction becomes more pronounced. However, it's important to note that this effect is only noticeable at extremely high speeds, well beyond our current technological capabilities. An interesting consequence of length contraction is that it affects distances between objects in the direction of motion. If you were traveling at light speed, the distance between objects in your path would appear compressed or contracted from your perspective. This means that the universe would seem more compact in the direction of your motion. As an object accelerates towards the speed of light, its mass appears to increase from the perspective of an observer in a stationary position. This effect is known as relativistic mass increase. To understand this concept, we need to dive into Einstein's famous equation, E equals mc squared. According to this equation, energy, E, and mass, m, are interconnected. The equation states that energy is equal to the mass of an object multiplied by the speed of light squared, c superscript 2. The speed of light, c, is a fundamental constant in the universe. As an object accelerates towards light speed, its kinetic energy increases. According to the equation, this increase in energy corresponds to an increase in mass. The closer the object gets to light speed, the greater the increase in mass. It's important to clarify that this mass increase is not a physical growth of the object, but a relativistic effect. From the object's perspective, its own mass remains unchanged. However, to an observer outside the object, the mass appears to grow as the object's velocity approaches the speed of light. As an object with mass approaches light speed, the energy required to accelerate it further becomes exponentially larger. In fact, as an object with mass approaches light speed, the energy required to reach or exceed light speed becomes infinite. This means that it is theoretically impossible for anything with mass to travel at or exceed the speed of light. This limitation arises from the fundamental properties of spacetime and the laws of physics as we currently understand them. The relationship between energy, mass, and the speed of light is a key aspect of Einstein's theory of relativity, which has been extensively tested and confirmed by numerous experiments. The Doppler effect describes the change in frequency or wavelength of a wave as a source of the wave moves relative to an observer. Let's focus on its manifestation in light waves as we travel at high speeds. When you're moving towards an object, the light waves emitted by that object become compressed or squeezed. This compression leads to a decrease in the wavelength of the light waves, resulting in a shift towards the higher frequency end of the electromagnetic spectrum. This phenomenon is called a blue shift because light with shorter wavelengths is associated with a bluish hue. Conversely, when you're moving away from an object, the light waves become stretched or stretched out. This stretching leads to an increase in the wavelength of the light waves, causing a shift towards the lower frequency end of the electromagnetic spectrum. This effect is known as a red shift because light with longer wavelengths is associated with a reddish hue. The Doppler effect occurs because the motion of the observer and the source of the waves alters the perceived frequency or wavelength of the waves. As you move towards a light source, the relative motion between you and the source compresses the waves, resulting in a higher frequency. Similarly, moving away from the source stretches the waves, resulting in a lower frequency. This effect has been observed in various astronomical contexts, providing valuable insights into the motion and behavior of celestial objects. For example, astronomers use the redshift of light from distant galaxies to infer that the universe is expanding. The farther a galaxy is from us, the greater the redshift in its light, indicating that the universe is undergoing expansion. As we mentioned earlier, the energy required to accelerate an object with mass to the speed of light is theoretically infinite. This means that achieving light speed travel would demand an unimaginable amount of energy, far beyond our current technological capabilities. To understand this concept, let's refer back to Einstein's equation, E equals mc squared, which relates energy, E, to mass, m, and the speed of light, c. According to this equation, as an object with mass accelerates towards the speed of light, its energy requirements increase exponentially. The closer the object gets to light speed, the more energy is needed to accelerate it further. At speeds approaching light speed, the energy required to propel an object becomes enormously large. For example, even a small object like a spacecraft would require an astronomical amount of energy to reach just a fraction of light speed. This energy requirement would grow exponentially as the object approaches the actual speed of light. The reason for this immense energy requirement lies in the nature of mass and energy. As an object accelerates, its energy increases, and according to Einstein's equation, this increase in energy corresponds to an increase in mass. Therefore, the more energy is needed to accelerate an object, the more its mass increases. As an object approaches the speed of light, its mass would theoretically become infinite, making it impossible to accelerate further without an infinite amount of energy. Practically speaking, the energy requirements for light speed travel are currently insurmountable. Our current understanding of physics and technology does not provide us with the means to generate or harness the immense amounts of energy necessary to propel objects to such velocities. Thank you for joining us on this exciting adventure. If you enjoyed this video, be sure to like, subscribe, and hit that notification bell to stay up to date with our latest scientific explorations.